Good evening, and we're going to mainly focus on weeks 7 and 8. It's sort of, I would classify them as slightly dry weeks in the sense of, I know the topics are a bit more technical, but important nevertheless, very important in how probability relates to IID samples, and that's a huge connect to the real life and how you make that assumption and go forward. Okay, so let's get started. I wanted to just share a few very, very important things that the way we use them, at least in this class, there's this moment generating function. We use very, very little of it, but generally it's defined like this for discrete random variables. It's basically expected value of e power tx. And crucially, if you add IID random variables, then the mean MGF multiplies. Okay, so that has a nice effect. The way we define weak law of large numbers is through this Chebyshev inequality. So we have this the way in which we look at the so we say the t by n sort of tends towards e of x. So it takes values close to e of x, and that's a weak law of large numbers. And the Chebyshev inequality sort of quantifies that. So using the WLN, when we say whenever we use WLN, LLN in this course, at least we're using the Chebyshev inequality with the variance. Okay. And then even more powerful in practice is the CLT, which approximates sums of IID random variables to the normal distribution with mean n times the mean and variance n times the variance. Okay, so or you could do t by n, in which case you would get something else. So the variance standard deviation goes a square root, and that is something to be careful about in the way we think about it. So actually, if you divide by root n, then you get a constant variance. The variance becomes exactly variance of x. If you don't divide by n, the variance keeps growing. If you divide by n, the variance keeps falling, right? So that's the thing, and it's very powerful, very, very powerful result. Okay, so having said all this, so let's jump into some sort of textbook type problems which use these ideas so that you get familiar with how to use them, how they show up, and how to work with them, etc. Okay, so the first problem I'm going to put out is a very, very straightforward MGF computation. It's a discrete distribution with x equals -1, 0, or 1. And those are the probabilities: 1 by 4, 1 by 2, 1 by 4. And would like you to write down the MGF for this random variable. Okay, so there are actually very, very, very few students who've signed up on joinpd.com. There are only about 6 people there. So maybe we'll go very quick. So I think if more people join, maybe we'll see more responses. So I'll wait for some 2 or 3 responses and keep carrying. You have to go to joinpd.com and The code is right there on the right top, YGEKCL. And okay, so there's about 5 responses. I guess one can't expect too many, given maybe because people are doing other things. So let's go on and see what the answer is. I think one is very correctly written by one person. Somebody has written 0.5. Okay, so that's not correct. The moment generating function will have one variable, and you have to multiply it out. So out of the responses, the 3 of them are correct. 1 by 4 e power minus lambda and plus half plus 1 by 4 e power lambda. Okay, so that's good. That's good to see. So it's just a straightforward discrete distribution. You should be comfortable doing MGF for this. Now, one of the utilities of MGF is it captures sums of IID random variables in a slightly, I don't know, in the small case, I guess it's a bit trivial, but still, it's good practice to see how to do this. So you're given a distribution X, then the same as last time, and then there is X1 and X2, which are IID according to X. And then what are the MGF and PMF of X1 plus X2? There's multiple ways to do it. You can make a table and do it. And the table will have 9 entries, and there are 3 into 3, right? So then you have to look at all the sums and write down. That's one way of doing it. But with the MGF, you can sort of keep track of everything in one go, then multiply it out. Okay, so basically X1 plus X2, the MGF of X1 plus X2 is the product of the MGF of X1 and the MGF of X2, right? Now, MGF of X1 and MGF of X2 are the same because they're both the same distribution. So you just take the MGF of X and square it. You will get the MGF of X1 plus X2. Okay, so it's a lengthy expression. By the time you type it out, it'll probably take a long while. Okay, so I hope somebody can write it down reasonably. Should be good enough. Okay, you can use L for lambda if you like, or you can use T instead of lambda. All of that is possible. Let me wait for a couple of more responses. I guess people are typing maybe furiously. Okay, so I think it's good to see what it is. Okay, so there you go. So that's the square. Okay, that's correct. This is MGF of X, and then you have to square it. Okay, so to get this. Oh, somebody has done hyperbolic cosine simplification. That's very nice. Square of previous response. Wow, very nice. That's a smart piece of answering. Okay, so how will you do this one? Okay, so that's the previous one was okay, straightforward in some sense. You just square the previous one. How will you do this guy? X1 plus 2x2. Is this easy enough, or do you have to do something else totally different? MGF and PMF of X1 plus 2x2. So normally you can treat these kind of questions as functions of 2 random variables and write down your table method. It'll eminently work. There's nothing wrong in doing that. But this is, of course, an MGF question. So hoping you can maybe use a bit of MGF in your answer. Okay, I'll wait for 2 or 3 responses, then go through to the next one. So this is pretty much the level at which I will expect knowledge of MGF, nothing much more deeper than this. It's a bit of a difficult area, a bit more technical than what we can do in this course, in some sense. Wait for a couple of more responses and then move on to the next one. So be careful. I mean, don't simply raise the MGF to the power 3. Okay, that's not the answer. So it's only independent. If you do x1 plus x2 plus x3, yeah, of course, if they're all IID, then you can raise it to the power 3. This is x1 plus 2x2. So you have to treat x1 as one of the random variables and treat 2x2 as another random variable. So what's the distribution of 2x2? You have to find the distribution of 2x2. And that will take values -2, 0, and 2 with what probabilities? 1 by 4, 1 by 2, and 1 by 4. So once you write that down, you can write the MGF for 2x2. You can write the MGF for x1 and then multiply those two guys to get the MGF for x1 plus 2x2. Okay, so it's a bit of a slightly more elaborate process. You have to combine multiple ideas that you had from previous weeks and this week to get to the answer. Okay, I hope that's all right. And let me see. Cube of solution 1a. See, that's the mistake. I think quite a few of you are saying MGF cubed. That's not correct. This is the correct answer. So you see the answer here. So you have to carefully take the 2 times x2. 2 times x2 is not just, you can't square it. I think a lot of people who wrote that is wrong. I think if you wrote MGF cube of solution for 1a, that's not correct. Because x1 PMF is 0. No, it's also not correct. Yeah, so this is the correct answer. This answer is the correct answer. So let me also show you how this is worked out. So hopefully you see why cubing the MGF is not the correct answer, right? Because it's x1 plus x2 plus x2. x2 is not independent of x2. There's no independence there. So you can't just multiply. You have to think of x1 as one random variable, 2 times x2 as another random variable. Find the MGF of each of them and multiply. Okay, that's why I think it's important to know how and why you're using the results. Let me just quickly show you the solution that I have. So the solution I have, the first question, finding MGF, it's basically MGF is expected value of e power tx. So you can also write lambda x. I think maybe in the lectures I write lambda x here. So lambda, put t here. It's probability that x equals -1 times e power t times -1. So it's expected value of a function of x, right? So this is all you do here. Probability that x takes a value and then evaluate that function at that same value, -1, 0, 1. Just add it up all together, you get this expression. Okay, watch out for that. It's in some, I mean, I think some people might have cancelled e power minus t and e power t. So see, e power t and e power minus t are not negatives of each other. Okay, they are both positive. Okay, so be careful about that kind of thing. And then x1 and x2 are IID x, and then what's the MGF and PMF of x1 plus x2? Here you can multiply the MGF. Since x1 is independent of x2, both are identical, so you just square the MGF, you will get it. And from there, from the MGF, you can read off the probability mass function as well. Now, when you do x1 plus 2x2, you have to be careful. Okay, so you have to multiply the MGF of x1 with the MGF of 2x2, which is not the square, right? So it's a different expression. And once you simplify, you will get the PMF as well. Okay, I hope that's clear enough. There were a couple of questions on chat. I don't know if I should see that. Yeah, I think T is good. And we say MGF of 2 by 2, 2x2, okay, as sigma P of X. Okay, so in this case, yes, I think, yeah, 2, because this multiplication by 2 is a one-to-one map. So yes, you can do this. This will also work out as the same value. Okay. Okay, good. So let's move on to the next one. We're going to jump into weak law of large number type question. Okay, so basically dealing with sample statistics, descriptive statistics of samples, and how to do things, etc. So here again, I'm starting with a simple discrete random variable. It takes just 3 values. Okay, and there are n IID samples from this distribution. Okay, 1, 2, and 3. Just 3 values with different probabilities there. And then I'm looking at the sum. Okay, so this is the statistic I'm looking at, x1 plus xn. What is expected value of t? What is expected value of t by n? Very simple question. I hope this can be quickly answered and we can move on. Okay, so about 10 answers. I'll wait for a few more answers to come in. This is a relatively easy question. Don't want to spend too much time. So all you're doing is using linearity of expectation in some sense. You need to find expected value of x. So that's like this little computation with the value of x and the probabilities. Get that. Okay, so it's about half the people have responded. So let's look at it. Okay, n times e of x. Okay, it's all right. 5 by 3, 8 by 3, 8n by 3, 5 by 4, 5n by 3. So if expected value of t is 5n by 3, why did expected value of t by n become 5 by 4? I'm a little confused by that, right? So, okay, there you go. It's a correction. I'm happy. 5n by 3, 5 by 3, n into half plus 2 by 3 plus, okay. So people are refusing to do calculations, adding fractions. 5 and 5 by 3 is not quite correct. So the correct answer is this guy, right? So n times 5 by 3 and 5 by 3. That's it. And there's no lambda here. There's no MGF. I'm not asking anything like that. I don't know how people got 5 by 9. So 5 by 3 and 5 by 3n? No, 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 no. I think, again, there's some confusion there. N times 5 by 3, 5 by 3. So this is the correct answer. N times 5 by 3 and 5 by 3. Okay. So this is just the sum, right? T was just the sum. It was not divided by n by itself, right? Keep that in mind. So expected value of t will be n times 5 by 3 and expected value of t by n will be 5 by 3 itself. Okay, so I'll show you the solution in a little while. Let's do a small variation on this. Okay, same question, same distribution, different question. What is the variance of t and what's variance of t by n? So we saw the expected value of t was, was growing as 5n by 3. As you got more and more samples, the sum was blowing up. But expected value of t by n was a constant. It became 5 by 3 as you keep getting more and more. If you do t by n, you get a constant in expected value. This variance will show slightly interesting behavior between variance of t and variance of t by n. There is something in between that will be constant. For instance, a problem that I didn't post here is variance of t by root n. And that will end up being a constant. Okay, let me wait for a few more responses. So when you add IID independent random variables, the variances add. Okay. When you divide by a constant, what happens to the variance? It gets divided by what? The square of that. So you have to use that fully. Yeah, that's true. Square of the constant, that's true. Okay, so we've got about half of people responding. Yeah, okay, that's good. That's good. 5n by 9 and 5 by 9. See, that's where I think a lot of people think variance is like expected value. See, there's a square in the variance. Okay, so behavior changes. Variance of t is 5n by 9. That's okay, but variance of t by n is not 5 by 9. It doesn't become a constant. It actually 7 by 18, 5 by 3 and 5 by 3. And I'm not seeing the correct answer. Ah, there you go. Finally, after a lot of answers, I've come to the correct answer. 5n by 9 and 5 by 9n. That's correct, I think, at least. Okay. So the variance of x, everything hinges on finding the variance of x correctly. You find the variance of x, and then variance of t is n times the variance of x. Okay. But when I divide by n, you have to divide by n squared. So you will get a divide by n. So what will happen, what's interesting, if you want a constant here, you have to divide and find variance of t by root n. Okay. So that's why the square root n keeps showing up in many of your CLT formulae and all that. So these are things to think in this, remember in this way, these summations scale. Okay, so let me show you the solution just to drive home this point. It's important that you get a good hang of this, because this will come over and over and over again. The first step, of course, is to find the expected value. That's easy enough. The next is to find the variance. I don't know, different people use different methods for finding the variance. The one I like is to find the expected value of x. Next, find expected value of x squared. Okay, that's usually easy, 8 by 3. But you see, a lot of people gave the answer as just 8 by 8, n by 3, and 8 by
Sir? Not audible.
Hey, hi. I'm not able to hear anyone. The call going on.
Yeah, I think we're all waiting.
Yeah, Andrew sir has some network issues, right? Sometimes he mentioned in the previous call that there are some broadband issues. So we're waiting for him to join back.
Okay, is this better? Finally? Okay, finally. All right, let me share my screen and let's hope and pray that the network treats us better. All right. So there's a bunch of questions about people saying, what is the question? My lectures, then you probably don't see it. It's when I say it's IIDX, then every xi is distributed the same Okay, can you hear me now? Is this okay? Does it seem okay?
Yes,
Okay.
sir.
All right. I've given up on the IITM network. I'm connecting through my hotspot on my mobile. So I'm not going to start video just for conserving bandwidth. I'll share my screen. It should work. This is usually not so expensive. Okay, so let me repeat the nature of this question. So you have 1, 2, and 3, and these n, there is n IID samples of this distribution X, as in n could be 1,000. Just think of some very large number, if you, or maybe a small number, 10, if 10 sounds better to you. So you have n IID samples of X. So each Xi is a random variable. Okay, each xi is a random variable. So t is also a random variable. T is x1 plus x2 xn. So each xi has the same distribution as x. X1 could be 1 with probability half. X1 could be 2 with probability 1 by 3, 3 with probability 1 by 6, and so on. Same thing with x2, same thing with x3. So let me ask a question here which you can answer in chat. How many possible different samples can I get in this sampling, in this kind of distribution? Let me see if somebody remembers their counting from stats 1. How many possible samples can I get? 8? Really? 8? Really? There are n IID repetitions of this distribution X. Each value is it 3 times n? Really? 3 power n, right? Finally, Ritodeep has got the correct answer, right? Why is it? No, it's not n power 3. It's 3 power n, right? See, every xi could be one of 3 possibilities. It could be 1 or 2 or 3. And then, 3 into 3 into 3 into 3 n times. So there are so many samples that are actually possible, n samples. Okay, keep that in mind. Everything will have a probability and all that, and you can do all that calculation. Okay, but we're not interested in all that. We're just interested in the sum, x1 plus x2 plus xn. And when you do the sum, there are some nice simplifications. Expected value of t becomes very simple, like in the last example. Variance of t also becomes very, very simple. So variance of t is simply the sum of the variances. If it is just the sum of independent random variables, and you divide by n, you just divide by n squared. Okay, so if you see the solution, that's all that I use here. Very simple way to write the solution. Variance of x, and that comes as 5 by 9. So variance of t is simply n times variance of x, and that's just 5n by 9. Variance of t by n is variance of x divided by n, and that's 5 by 9n. Okay, so hopefully you see the contrast between expected value and variance. Expected value of t grew as n. Variance of t also grows with n. Okay, 5n by 3, 5n by 9, that's okay. But expected value of t by n itself became a constant, and variance of t by n became, on the other hand, 5 by 9, and it's falling with n. Okay, so only variance of t by root 10 will be a constant. So this is a nice sort of thing to remember in your head, and then how it works. There was a question on chat. I'll take it up a little bit later. Let's move on to the next question. Okay, so here's something to do a little more. Okay, so I think you understand what I mean by IID samples and all this. Try this one. Let me see. Some question on chat. Wow, Dhanush, you've asked a very complicated question. Is there only infinitely many samples? Okay, redundancies. So the word redundancy is a bit vague in that question, and we're not talking about things like redundancy in data in this course. Maybe as you do more courses, you may come across ways of quantifying things like redundancy. As far as we are concerned, each xi is independent, so it carries with it some information about the distribution, and that's what we are concerned about at this point. Okay, so at this point, we're just looking at descriptive overall statistics like the sum and moments and things like that, not anything else. So let me see. Okay, so please don't put the answers here on the chat window. You have to go to joinpd.com, then enter your answers on that. The code in joinpd.com is given on the top right, YGEKCL. Okay. We wait for a few more responses. So there's a question from Harshita, which is interesting. So in your opinion, statistics 2 is very hard, is it? Okay. So I don't think you do any more stats courses after this. This is the pure stats course wise, this is the only one. The next one is a course called ML Foundations, Machine Learning Foundations. That will have a fair amount of theory in it, slightly more advanced linear algebra, slightly more advanced probability, slightly more advanced optimization. All three you will do in that course. That's going to be a bit of a challenge. So again, I would tell you, I think many of you, I think, got very there's a question from CS Shruti. I think I we can add IID variables. Anand is saying something, is sampling. So what is the question? I'm going back up all the way to find the question. Shruti, I did remember seeing it.
1932.
Yeah, just hold on. I try to scroll up, but then somebody else comments, and then it comes down to me. Sorry about that. Why can't we add non-IID variances? Is that the question? Sum up expectations even if they are non-IID. That's true. Okay. Yeah. Okay, so let's come back to the answer. I've given enough time. I think enough people have responded. Let's see the responses. It's n by 3, 1 by 3, n by 3, 1 by 3, 10 n by 3, and 10 by 3, n by 3, 1 by 3. Okay, so enough people have got it right. It seems like people are happy. With the squared is a very easy distribution, isn't it? It's just 1 by 3 with probability, 1 with probability 1 by 3 and 0 with probability 2 by 3. It's actually Bernoulli. X squared is Bernoulli. So it's very nice to see and get it out. So let's try the next one. Okay. I'll answer some of these questions while you try the next question. Okay. So John Rice is a book that I like. I don't know if other teachers will use that book. There are other books as well. So many other books. Some sense. the concepts that sound a bit abstract, uh, uh, they'll some of these ideas, as you you're saying, you're all studying in estimation, ideas like confidence intervals and this notion of the use of data and imagining that to be samples from some unknown distribution, and what does that mean, right? I think Shruti was asking something about difference between samples and samplings. It's sort of, I mean, nobody will. I think this word sampling is something that I use. I think most textbooks will not even bother to differentiate between the capital X1, capital X2, capital Xn, which is actually a sequence of random variables, with the actual samples you may get, 1, 2, 4, 5, whatever, right? The numbers. They will call both as samples. And I think it's okay. After a while, you'll get used to it. You'll know when they're talking about data and when they're talking about the random variable that is samples. It takes some time to get used to. Okay. All right. So only 6 people have responded. Suddenly, variance seems a little bit more difficult. Oh my God, I don't know this course from MIT OCW. The data science or programming. I think programming should go first. That's my opinion. The data science can come next. You can do a little bit of both in parallel if you like. That's also possible. I did not change the question. No, I'm not. I'm still in that variance of M2 and variance of M2 by N. So let's go to the answer. Yeah, okay. So people have got it. 2n by 9, 2 by 9n. 2n by 9, 2 by 9n is correct. 2n by 9, 2 by 9n is correct. There's also some 8 by 36. I don't know where that came from. Watch out on how you've done this. Okay, good. I think there are enough people who've got the correct answer. Let me just quickly show you what the thing is. I think I didn't renumber this question, right? I made it also Q3A, it was actually Q3B. Sorry about that. The actual question is different. Okay, so let me show you the solutions that I have real quick. Q3B. Okay, 8 by 36 is 2 by 9, of course, absolutely. So 1 by 3 ends up being the mean of x squared. So mean is n by 3, 1 by 3. It's easy enough. So variance is a little bit more clumsy computation. You should be slightly careful. You can do that. You'll get 2 by 9, 2n by 9, and 2 by 9. Okay, good. So let's move on to the next question. Okay. So this frequencies are important, quite important. This is something that you'll always get when you're looking at discrete distributions and sample DI-ID. And I've never really talked about frequencies in this class. It's slightly more, it's not that different. Frequencies form a very important part of your descriptive statistics in some sense, right? So if x is a random variable, it's discrete, it takes just 4 values, and fi is the number of I in the sample. So f1 is what? How many ones are there from x1 through xn? f3 is what? How many threes are there from x1 to xn? Okay. So this is, I mean, you go ahead and do it, and then I'll comment on the answer a little bit. So this is sort of at the heart of weak law of large numbers and many interesting things. Frequencies are very important. Frequency is not an indicator. Frequency is a sum of indicators. This needs a slightly different modification to the x1 through xn. You have to sort of modify it into a Bernoulli sequence. For f1, to find f1 is the sum of n things. You have to basically see, is x1 equal to 1, right? Then you add a 1, right? Is x2 equal to 1? Then you add a 1 to the f1. Okay, so f1 is actually sum of n Bernoulli random variables. What is that Bernoulli random variable? How do you go from that from x to that is the question. Question from Shreya, which again is the idea of multiplying by n. That is, n becomes large, the mean or variance convergence to multiplying by 1 by n, you mean, right? So you're dividing by n. Yeah, that's true. That's true. The division by n tends to make it finite in some sense. Yes, you will have a formula sheet. You don't need to remember formulae. Okay, so about 7 responses. It's a relatively easy question, but anyway, I think this is the first seeing this word frequencies. Maybe it's a little bit distracting, but don't worry about that. It's just f1 is the number of ones that show up in the sample. F3 is the number of ones that show up. On average, what should it be? I mean, just think about it. Intuitively, if you were to answer, if your distribution has every sample is probability 1 by 6 of being a 1, and you do n independent samples, what is your expected value for the number of ones? It should be n by 6, isn't it? There's no major mega theory in that. It's some very simple thinking, right? It should be n by 6, isn't it? So that's the sort of meaning of the probability itself. Same thing with expected value of f3. It should be n by 3, isn't it? Every sample is likely to be 3 with probability 1 by 3. So that's the same thing expressed in one more complex format is what I told you about indicator, random variables, and this and that and the other. Okay. Okay, so let me see the responses. They're not coming in really very fast. People seem to be okay. So n by 6, n by 3, whoever has got it, but yeah, so look at that. Expected value of fi is simply n times probability of xi. So this is the essence of probability, okay? So this fact that the number of times when n becomes very, very large, number of times I occurs divided by n is probability of xi, right? So that's exactly the definition for probability. So this n by 6, n by 3 and all should come very, very close, right? So people have got that right. So I really like this answer, very clean answer, just 3 lines. It clearly conveys what they want to say. Okay. So what happens is n becomes very, very large. What should happen to the variance of f1 and variance of fn, f3? So let's do that in the second problem. Okay, the same question. Fi are still the frequencies of I. What is variance of f1? What is variance of f3? Okay, does the seem all right to you? Are you confused about how to go to variance? So there's a trick here. You have to express F1 and F3 as the sum of n Bernoulli random variables. That's very important. Once you do that, then you can quickly get to the answer. If you don't, you'll be going round and round thinking about how to find variance. Okay. F1 is the sum of n Bernoulli, independent Bernoulli 1/6 random variables. F3 is the sum of n independent Bernoulli 1/3 random variables. Okay. Once you realize that, the answer will be very, very fast. Okay, so let me quickly see what the answer is. Approach is 0. Okay, not really. That's not true. So the variance goes as 5n/36, 2n/9. That's correct. I think some people have got it right. 5n/36, 2n/9. Remember, this is just the variance of the sum. I'm not dividing by n. Why will it fall down to 0? It won't fall down to 0. It's 5n/36, 2n/9. That's the correct answer. Okay, so let me just close this and then show you my solution. So this is the solution. I've written it out in detail here. Notice here, to get F1, what I do is I define this x11, x21, xn1. I'm just calling them as that way, where this xi1 basically is equal to 1 if xi is equal to 1. It is 0 otherwise. So basically, these are all indicator random variables that indicate whether or not the ith sample was equal to 1. Okay, so I just add them all up, I will get F1. Okay, so this way, expected value of F1 is simply n times expected value of x11, and that's n/6. So this is just Bernoulli 1/6, a very simple and direct way to get to the answer. Okay, once you write it like this, the F3 is also very easy. You say quickly it's n/3, and then the variance becomes 5n/36 and 2n/9, just because of this Bernoulli distribution. So notice how the standard deviation is square root, right? So if you take standard deviation of F3, F1 deviation of F1 is some square root n, and expected value of F1 is n/6. Okay, so as n becomes really, really, really large, the F1 is going to sort of concentrate around n/6, isn't it? So that's the essence of weak law of large numbers. So this is sort of an important thing to remember, and quite intuitive. Okay, so that's something nice to know. Okay, so now I think we're going to move on to weak law of large numbers and finding bounds on probabilities and approximate or estimating probabilities using CLT, and bounds on probabilities using weak law of large numbers. So I keep saying weak law of large numbers. I really mean Chebyshev inequality. I hope I hope that's clear to you. But in our course, at least, we've been calling it WLLN. So here's the question. You have this is actually the same random variable as before. A while back, we used the same case, and I'm looking at this sum t, and I want you to get a bound for t greater than 2/n. If you remember, the expected value of t was 5n/3, which is lesser than 2/n, right? So I want an upper bound for probability if t greater than 2n. And this one is using weak law of large numbers, so you need to use Chebyshev inequality basically. So a couple of live sessions back, we did an entire session on Chebyshev and Markov. I gave so many questions on it. But when we ask it in a slightly different guise, it seems like a new problem totally, maybe. I don't know. So it's just you have to find expected value of t, variance of t, and then convert this event t greater than 2n to something like, no, mod t minus expected value of t greater than something, then you use Chebyshev directly, right? So that's this weak law of large numbers. The responses are slowly trickling in. People are a little confused as to how to do this. So maybe I should show the solution. Let me just see the responses. I think many people are confused by this. So answers are going sort of all over the place. Let me show you what I was expecting from a question like this. Okay, so look at this. This is sort of the answer that I want. So it's very simple. Not more than Chebyshev equality things, but not so confusing to you. So we saw this calculation before. We came across this random variable before, but even otherwise, it's a simple enough random variable. You can quite easily find expected value of t and variance of t. You saw this before, right? 5n by 3 and 5n by 9. So that's the first step. The first step in using Chebyshev, or what I call here is WLLM, is that. Okay, the next step is to convert this event t greater than 2n into a form where Chebyshev inequality can be applied. We did this a couple of sessions ago. I gave so many questions which like this, right? So t is greater than 2n is sort of the same as t minus 5n by 3 is greater than n by 3. So why am I subtracting 5n by 3? Because 5n by 3 is expected value of t, okay? And this guy is contained in absolute value of t minus 5n by 3 greater than n by 3. Okay, so this is the crucial step. Okay, once you finish this crucial step, probability of t greater than 2n is less than or equal to probability of this guy. Now, probability is a classic Chebyshev form. It's less than or equal to variance of t, which is 5 by 9, divided by n by 3 squared. So 5 by n. Okay, this is the answer that you get when you do this straightforward sort of application for weak law of large numbers. So I keep saying weak law of large numbers, but really, I mean, these kind of questions are Chebyshev inequalities. But since we saw this in the context of weak law of large numbers, I'm putting it up. So the probability that this t becomes bigger than 2n falls with n as 5 by n. Okay, in fact, maybe there are sharper bounds, but at least falls with n. Okay, so this is what you have to do if you have to find an upper bound using weak law of large. This is not very different or difficult from the Chebyshev inequality. We did so many problems on Chebyshev inequality a couple of live sessions ago. This is sort of similar to that. Okay, I hope it's clear. Okay, now this part B to this question. Okay, so maybe I should go back to the responses and see 5 by n. Somebody has got 5 by n, 5 by n, but lot of 5 by 9 and 15 by 9 n squared. This lot of n squared n cubes in the answer. Pay attention to how you did it and take a look at the solution. It's in some sense it's simple. I think it's you have to pay attention to factors and use what you do. Okay. So the next question is probably more important. This is the sort of calculation that you may be doing. Same distribution before. Now using CLT, central limit, CLT is central limit theorem. You have to find an estimate for t greater than 2n. Now your answer you have to express in terms of fz, right? You remember fz in the previous live session, I spoke about this FC, that is the CDF of the standard normal. Okay, so express your answer in terms of FC, but find an estimate for probability of t greater than 2n. Okay, so you use CLT now. Again, CLT will need mean and variance, right? You remember the mean and variance for t. Once you find mean and variance, you can use CLT. I'll also show you the solution. These are actually simple arithmetic steps, but it's good to see them once and make sure you get the right answer. So CLT basically says t is going to be approximately normal with mean n times expected value of x and variance n times the variance of x. That is essentially the central limit theorem. So t is approximately normal with mean n times expected value of x and variance n times variance of x. Okay, so you make that normal approximation and then try and compute this probability that t is greater than 2n. How do you do? This is just a normal interval calculation, right? There are so many normal interval calculations that we have done. So you just use that. Okay, so I don't know, some of you complained about a lot of jargon coming out, but you see essentially everything is a probability calculation, and invariably it's just a matter of understanding what the event is, adjusting the event to get to something that you want, and reusing the same things over and over again. So they're not different fundamentally. I hope you see that. This is important. Okay, so I'm going to take a little bit of time, give you some time and get a sense of how you use the CLT to estimate these kind of probabilities. This is a very, very, very important skill. Okay. Once again, like I told you, the thing to remember is t is approximately normal with mean equal to n times expected value of x and variance equal to n times variance of x. So you just find the new mean and variance of this normal approximation and then simply use directly what you have to do. But I think I do see people are struggling a bit. Maybe I should show this solution for the first time and then give you the problems practicing. So here is how I would write it down. T is going to be approximately normal with mean 5n by 3 and variance 5n by 9. So this is the central limit theorem cast in a different way. Okay, so I might have stressed several other things in explaining CLT about the root n scaling and this and that and the other, but this is essentially how you use it, right? So when you just take the sum, this is how you use it. T is roughly normal 5n by 3, 5n by 9. This is what I wrote down in my very first slide, right? In CLT, when you take just the sum of n random variables, it's normal 5n by 3, 5n by 9. After that, calculating the probability is the classic probability calculation for normal distribution. So t greater than 2n, how do I do? I convert it into the standard normal. How do I convert it into standard normal? T minus 5n by 3 divided by root 5n by 9. So t greater than 2n is equivalent to that, which is t minus 5n by 3 by root 5n by 9 greater than 2n by minus 5n by 3 by root 5n by 9, isn't it? So once you do that, you will get some cancellation happening here, and you will end up getting square root of n by 5. And so this is z now, right? This t minus 5n by 3 by root 5n by 9. So probability t greater than 2n is the same as probability that z is greater than root n by 5. Okay, and so you get 1 minus fc of root n by 5. Okay, isn't there a square root n in the denominator? Denominator of what? I don't think so. I don't think I've missed any square root n's in the denominator. Let me see the answer that people have given. Let me see if anybody has given an answer like this. There are about 10 responses. Yeah, so you see 1 minus fc of root n by 5. I think the root will come inside the n by 5, not outside. Okay. 1 minus fc of root n by 5. So quite a few people have got 1 minus fc of root n by 5. Quite a few people have got other factors. So there's a question on the. So there's a question about t minus mu by. Okay, so it depends on what you call mu and what you call sigma. You have to pay some attention there. Be a little bit careful with this. See, once I have a normal distribution, once I'm thinking of a normal distribution with mean mu and variance sigma squared, t minus mu by sigma is standard normal. Okay, that's the best thing to remember in my opinion. Okay, whether you're doing CLT or anything else, best thing to remember is that. Okay, so you may want to approximate t with normal, or you may want to approximate t by n with normal. But whatever you do, you'll get the same answer, right? Eventually, the answer will be the same. So you may say t is approximately normal 5n by 3, 5n by 9. You could say that. Or you may say t by n is approximately normal with mean 5 by 3. And what will happen to the variance? Watch out there. It will be 5 by 9n. N will come in the denominator there. Okay. So that's when you do t by n approximation. Or you may approximate t by root n. If you approximate t by root n, what will happen? You will get some, something in the mean, but the variance will be constant. Okay, so you can do multiple things there. It doesn't matter, but as long as you keep track of your mean and variance, you're going to be okay. Is that okay? I hope I answered the question very clearly. So when I'm saying t, I will have mean and variance as 5n by 3 and 5n by 9, normal approximation. If you say t by n, then the mean and variance sort of scale appropriately. Okay, I hope that's clear. Okay, so this is important. So Harshita, you're asking about a general rule like that. I think it's dangerous for me to give you a rule like that. Okay, so the rule is when I want to approximate t, which is some sort of a sum of n random variables, and I want to approximate it as a normal distribution, find the mean of t, find the variance of t. Simply say t is approximately normal with that mean and that variance. Okay, so if you say t, you're going to get 5n by 3 to be the mean, 5n by 9 to be the variance. If you say t by n, you will get 5 by 3 as the mean and 5 by 9n as the variance, right? So whatever you get as the mean of that, whatever you get as the variance of that, you can simply take as a normal approximation with that. Is that okay? That's the best way in which I remember it, and always that has helped me so far. So I think it's okay. Is that all right? Yeah, if you want to say t by n is normal, then you will get it to be normal with mean. No. When you consider t by n, you will get normal with mean mu and variance sigma square by n. Variance will be sigma square by n. It won't be root n. Okay. Okay, so that's the approximation. I'm not saying t by n is normal. I'm approximating it to be normal. Okay. Is that all right? When I do the calculation like that, it will work out like that. Okay, it's not normal. I'm not saying it's normal. It's an approximation. If you see, I'll put an approximately equal to. Okay. All right. So the point is, whatever you approximate, you could approximate t. You can approximate t by n. You can approximate t by root n. You can approximate t by n power 2 by 3. Whatever you choose to approximate, finally you will get the same answer. No, and the answer will always be the same because anyway, I'm defining my event with t. Okay. So don't worry too much about what you're approximating. As long as you're doing the algebra correctly, you will get the correct answer. Okay, let's jump into one more problem, the same type of thing, and we'll do WLLN and CLT. Okay, so try this one. Again, don't be thrown off by weak law of large numbers and all that. It's just Chebyshev inequality. Okay, so you have a random variable. In this case, you have just a slightly more complicated random variable t, which is the sum of n IID. And I want an upper bound for a probability of mod t greater than n by 2. And I want you to use the weak law of large numbers for it, which means, I want you to use Chebyshev inequality. Okay, so it involves finding expected value of t, variance of t, and then plugging in the Chebyshev inequality. There's nothing more to it, which we practiced quite a bit a couple of live sessions ago. So the same thing you should do here. So we're going to do the same. So in case you're done with this A part, part B is to find an estimate for the probability using CLT. Okay, so you can try that if you've finished the A part. I'll come to that the next one. So continuous uniform random variable, mean is a plus b by 2, right? So in this case, mean will end up being 0. Variance is b minus a whole square divided by 12. Okay. So in this case, variance will end up being 1 by 3. Okay. So the mean of x is 0 and variance of x is 1 by 3. I keep forgetting that I need to give you the formula, but by now I hope one of the things you should do is you should make a formula sheet for yourself, right? So you write down all these distributions, important formula, and keep it with you, quick reference. I guess if you did all that, you would be really happy in some sense. Yes, expected value of x is 0 and variance of x is 1 by 3. Okay, that's a p minus a whole squared by 12. It's continuous random variable uniform. So once again, just get a feel for what we are calculating here. T is expected value 0. So n by 2 is fairly large. I'm expecting each xi to be above half or something. So how does 12 come in the denominator? For the variance of x, you can prove it. It's just from the integration, I think. The expected value is a plus b by 2. If you do expected value of x squared, you're going to get x squared that you're integrating. So there'll be an x cubed by 3. And this, so it's going to be like a 1 by 3 in the expected value of x squared term. And there will be a 1 by 4 in the mean term. So you'll get a 12. Okay, so it's about 10 or 11 responses. I don't know if we're going to have the luck of having more responses than this one. Let me see, it's 2 by 3 n cube, 4 by 3 n squared. N cube and n squared and all look wrong to me. There's no fz here. We're not doing CLT yet. We're just still doing this. 4 by 3n looks correctish in some sense, but a lot of people are getting n squared. I don't know where they're getting n squared from. 4 by 3n looks right to me. Okay, so let's move ahead and do the same question, but now we'll use CLT. I'll show you the solution in a little while, but do the same question, same t, and the same probability, but instead of using weak law of large numbers, I'll find an estimate using CLT, and I will use the FC. Okay. How to find variance of unknown distribution? Why do you need to find that for this question? It's this is a known random variable, right? -1, 1. It's uniform in this one. Oh. Okay, okay. For some other question, I'll come back to that later then. Some extent, not now. Let's see. Okay, so let's see the responses a little bit. Okay, so we're getting f minus fc square root 3n, 1 minus 1 minus fc of square root 1.5 square root 3n and all that. So, okay, all right. So all over the interesting answers we've got, but let me show you the solution that I have, and maybe you can compare and see if you got the correct answer, got the same answer as I did. Okay, so this is the situation. X is a continuous random variable form in -1, the interval -1. So expected value, so t is a sum of n such IID random variables. So expected value of xi is 0. Expected value of x1 is 0. Expected value of x2 is 0. So expected value of t is also 0. Variance of t is n times the variance of xi, variance of x, and the variance of x is 1 by 3, so you get n by 3. Okay. After this, it's just Chebyshev. Okay, mod t greater than n by 2 is less than or equal to variance of t by n by 2 squared, right? And variance of t is n by 3, so you get n squared by 4, you get 4 by 3n. Okay, so it's falling with n. It's not very surprising. You get that from Chebyshev. Okay, so when you use CLT, what am I going to do? I'm going to approximate t as normal. So in case you're wondering, why is it that I'm suddenly able to approximate t or t by n or t? See, if I want a convergence result, I can't be writing things like this because this variance is blowing up. Okay, so when you want a CLT like convergence result, you have to look at t by root n. Okay, only then you will get a proper convergence to something something that is constant, something that is not blowing up. Okay, keep that in mind. So that's why CLT has that root n scaling. So if otherwise, when in calculus, you can take anything and approximate. Anyway, n is sort of finite, and this approximation will work anyway. Okay, in case that was bothering you, that was something to keep in mind. We missed the mod sign, hence the wrong answer. Oh, okay, yeah, so sure. The mod sign is very important. So if t is roughly normal, means 0 variance n by 3, mod t greater than n by 2 is the same as mod t by root n by 3 greater than n by 2 by root n by 3. Why did I do this? I want the standard normal. I want the z to come in, and this mod t by root n by 3, t by root n by 3 is fc. Okay, so you get the same as z being greater than root 3n by 2. Okay, so now mod z is greater than 3n by 2, greater than 3n by 2, or z could be minus 3n by 2. So you will get 1 minus fz of root 3n by 2 plus fz of minus root 3n by 2. Now fc is symmetric, right? It's symmetric about 0. So these two guys are exactly the same, whether greater than 3n by 2 or lesser than minus root 3. So 2 times fc of minus root 3n by 2. Okay. So I wish few people had got this answer right. Make sure you understand the region. At the end of the day, it's just a region on which you have to find a normal probability. I mean, all this other theory of where anything comes from is okay, but at the end of the day, it's just a probability computation over an interval. Okay, so keep that in mind. Don't make mistakes in calculations. Okay. All right. So next one is frequency. So I'm going to repeat the same thing. I think this is important enough that you should see it like 3-4 times and get practice. So I'm going to give you one more problem with the same idea. Now with frequencies. Okay, the same distribution we had before, same F5 we had before. Now I want you to do a Chebyshev upper bound on mod f1 minus n by 6 greater than 10 square root n. Okay. Is this the speed required for the exam as well? Oh my God. I don't know. I mean, how many? I think it's about 1 hour exam, right? I think there are usually about 10 questions or so, isn't it? You'll get about 5 minutes. So why don't you do the mock exams? The mock exams are out or not? Okay. So make sure you practice the mock as many times as you can. Time yourself. You can optimize your speed once you can time the mock exams well. Okay. So it'll improve. Speed is something that improves with practice. Frequency is a count. I mean, Fi is still a count, right? It's number of I in the samples. So it's a count. It's a frequency count. And the count is a random quantity in this case, right? When you have the samples being random, the count is random. So you see, the count is very important in many learning applications. So particularly, right, if you look at language modeling, where people look at text and try to fit probability models to it and all that, how many times a letter appears in a sentence, in a legitimate sentence in English, how many times a word appears, what are most frequent words. These things play a huge role. I mean, all of probability is actually glorified study of frequencies, isn't it? How often something occurs, and you have a theory built around it. So there's no wonder that weak law of large numbers comes in and confirms your intuition of frequencies and probability being connected, right? So it's very simple in some sense. Okay, so any luck with this particular version of the problem? In this case, the way I've put in the square root n, you'll see you will get a constant number. You won't get, I'm giving you a hint to help you get to the correct answer. In case you got an n in the answer, you're probably wrong. I've put a root n there, so the n will sort of cancel. Make sure you get a number at least, okay? So not to confuse anymore, Shruti, but you're confused about frequency. There's one more thing that a lot of statisticians study. It's called frequency of frequencies. Okay. Does that seem confusing to you? So instead of counting how many times a number 1 appears, they'll count how many numbers appear once. Okay. So that's called frequency of frequencies. And anyway, I think if frequencies is confusing enough, I guess frequency of frequencies is all the more confusing. But anyway, this is our course does not involve such things, so we can be happy. So see, you have to remember CLT is an approximation, okay, while Chebyshev is an actual bound, okay. So the range at which everything depends on how you're working. I think in sometimes CLT is good. Number one, sometimes Chebyshev is good because it gives you a bound. Chebyshev works for any random variable with a particular mean and a variance. CLT, it works only when you have sum of IID, isn't it? Right? And n becomes very large. That's when CLT kicks in. Chebyshev works for any random variable. So they have different realm of application. Okay. All right. There are about 7 responses. Things are going a little slow. I think people are a bit overwhelmed by the answer. The answer, like I said, is going to be a number. So hopefully that motivates you to get to the right number. Let me wait for a little while. Yeah, so when I ask for a probability estimate using CLT, I'll say estimate the probability using CLT. When I ask for Chebyshev, I'll say upper bound for P. So that sort of reinforces the notion of CLT being an approximation, while Chebyshev gives you a bound, okay, which is always valid. It cannot be violated. Okay, so about 10 people have responded. I think let me look at it in the interest of time because there's one more topic that we have not looked at. 1 by 720, it's absolutely right. What is 5 by 3600? It's also 1 by 720, right? So I think people have put it there just to confuse me. 1 by 720, that's good. There's no n. I told you there's no n in the answer. So 1 by 720, 1 by 720, that's good. I think most people have got 1 by 720. It's good to see where that would come from. Of course, part B is repeating a similar thing with CLT. Okay, using CLT, you find an estimate for probability of F3 minus n by 3 being greater than 10 times square root of n. Okay. We're at about 30 minutes to go. So I think there are about 4 or 5 questions. This is the last question on this WLN and CLT. We are moving on to the ML and MM estimation. I think those are probably a little bit simpler. We'll go through them a bit faster, I hope. Let's see. estimation is really interesting. Okay, good. Once again, I'm going to approximate F3 as normal. The mean of F3 is n by 3. We've calculated that before. And the variance of F3 is what? 2n by 9. You remember that? It's n times 1 by 3 times 1 minus 1 by 3, basically. So F3 is approximated as normal with mean n by 3 and variance 2n by 9, right? So that's the first step. And then you convert this event F3 minus n by 3, mod F3 minus n by 3 into, you have to get to that Z, right? You have to go to the standard normal. So you will divide by the standard deviation, root 2n by 9, okay? So then this becomes just mod Z greater than 10 times root n by root 2n by 9, isn't it? So so the root n will cancel and you will get something, and then from there you have to write something. Let me see. Given lots of hints here, so it's just careful redoing of. Okay, let me wait for 2 more responses. Once the responses hit double digits, I'll show you the responses and go to the solution. Okay, there you go. Hit double digits. 1 minus 2, okay, minus 10. Okay, all right. I think there are some answers which are sort of nearby. Yeah, 2fz minus 30 by root 2 looks correct. So that's correct. So let's go in and just let me show you the solution that I have. So since we are approximating using Chebyshev, so the value of f1 is n by 6, base n by 36, and probability of mod f1 minus n by 6 greater than 10 root n is less than or equal to variance divided by this guy square, right? 10 root n squared. You do the calculation, get 1 by 720. It's pretty fast. And then the next step is for f3 minus n by 3 greater than 10 square root n, and expected value of f3 is n by 3, variance is 2n by 9. So the CLT gives you normal approximation gives you normal n by 3, 2n by 9, and mod f3 minus n by 3 greater than 10 root n becomes mod f3 minus n root 3 divided by square root 2n by 9 greater than 30 by root 2, which you can also write as 15 root 2. So in some sense, oh, I made a mistake here. In the last step, I made a mistake. Apologize for that. Let me correct it right away. The last step is wrong, I think. This part is wrong. Up to the last part, I got thing, and then I made a mistake. So this part is not correct. This is not correct. So it's mod z greater than 15n by 2. So you'll get 2fz minus 15 root 2, isn't it? So this is what you would get. Yeah, everybody misses these things, except that you have to write exams, and I don't have to write exams to prove myself anymore. So it's good, right? So Let me just make sure there's something in my phone that's not connecting. So I'm sorry about that. Let me just connect hotspot. Okay. Yeah, I think it got corrected now. So that works out okay. All right. So let's move on to the next questions, which would come to estimation. Okay, so it'll be a very easy question. So let's go through this at a fast clip. I don't want to spend too much time on this. These are very, very basic and simple estimation problems. I've written enough exams in my life, so I think you have to write to support that online degree. I think I can't think of anything else right now. So you can write to supported online degree for any issue like this. Okay, so this should be very, very quick. There's only one response, really. Okay. Method of moments estimate for Bernoulli samples. Come on, by now this answer should be the most easy one if you've actually been looking at it. No. The method of moments estimate. You find the sample mean and then you equate it to the distribution mean, right? Expected value of x, and then solve for the unknown parameter. You get your answer. That's method of moments estimation. So in this case, the sample mean is 3 by 10. You equate it to the expected value of the distribution mean, which is P. From there, you directly get the answer. Okay, so it's as simple as that. So let me see. Most people have got it. 3 by 10, 3 by 10, 3 by 10, 3 by 10, 3 by 10. So it's pretty good. Let's move on to the next one. The same question, ML estimate. Okay, you've got a sample. What is the likelihood function? What is the ML estimate? I think the ML estimate is very easy. You even remember from the examples I do in my lectures or if you've seen my slides, but likelihood function may be a little bit tricky, but you can write it down. It's pretty fast. Okay. All right, let me go quickly see the responses. Okay, 0.27, really? People are still writing. I mean, okay, I guess you're really differentiating and doing something here, I think. Okay. So I think should not be okay. Let me get a little bit more time. Okay, look at responses. P power 3.3 power 3 and all is wrong. Okay, so P power 3, 1 minus P power 7. Okay. So looks correct to me. It's a correct likelihood function. How do you get to the ML estimate? ML estimate will also be 0.3 in this case. If you want me to look through the solution real quick, this is how I would write the solution for this problem. So n is n, and the moment is 3 by 10 is equal to the expected value distribution moment. x, and that's p. So p hat is 0.3. So first question. And the second question is p power 3 into 1 minus p power 7. That's the likelihood function. And then you differentiate. Differentiating always take log. So 3 log p plus 7 1 minus p. And 3 by p plus 7 by 1 minus p minus 1 is 0. You get 10. So this you may also remember by heart, but this is also possible. Okay. So let me just quickly go through a couple of more problems of this nature. This kind of question is sort of textbook and very important also. Okay. So same sort of question, except now the distribution is different. Okay. It's not standard Bernoulli. It is it's a random 1 or 2 or 3. Probability of 1 is by 3. Probability of 2 is t by 6. And probability of 3 is 1 minus t by 2. And actual samples are 1, 1, 3, 2, 3, 2, 1, 1, 2. Okay. Find the sample mean and find the estimate for t. Those of you who have done this question, you can imagine what the next question will be, right? It's very similar to part B of the previous question. So I don't see anybody who has done it. So let's see. How to decide which method is good to choose? Okay, between method of moments and ML, you mean? Okay. Interesting question. So it's actually depends on the problem. So in most cases, MM and ML may give you the same answer, right? I do a lot of derivations in my lectures. You'll see the method of moments and ML end up keep giving you the same answer, many cases. So that's one way of thinking about it. Either one would be okay. But supposing you just have data, right? You just have data. And in many cases, you don't even know what the distribution is, okay? So you have to choose a distribution, fit it, and then find its parameters, okay? So once you choose a distribution, the ML problem might invariably be too hard, or you may not even want to explore things like that. So in most cases, people end up choosing things like method of moments. Invariably, the answer you get will be close enough. So in this question, you're going to do both. You'll see it'll be close enough to the ML. So it's okay to use either one, I think. Okay, so there are about 8 responses. Hope no one complains about the use of calculator for such problems. Okay, be able to add this up quite quickly, I think. So about 10 people responded in the interest of time. Let me just go through and see it. 1.8, 18 minus 5t by 6, 1.68, 6 by 25, 0.96, 1.44, 1.255. Wow, 6 by 5 seems to be a popular answer. Sum of probability gives inconsistent equation. What happened? Did I make a mistake? It's not a valid distribution. No? I think it's correct. No, t by 3 plus t by 6 is t by 2. And t by 2 plus 1 minus t by 2 is 1, isn't it? I think it's okay. Looks fine to me. Okay. All right. I think people have given quite a few answers here. So maybe I should show the solution that I have. So what's happening? Okay, so M1, the sample mean is 18 by 10, which is 1.8. Remember, it's 1.8, it's 18 by 10. Okay, the mean is not 18, sum is 18, mean is 18 by 10. Okay, 1.8. That's going to be the distribution mean. You have to equate it to the distribution mean. That is t by 3 times 1 plus t by 6 times 2 plus 1 minus t by 2 times 3. That in my calculation worked out to 3 minus 5t by 6. Okay. Did I make a mistake here or is that okay? Okay. 3 minus 5t by 6. So I equate 3 minus 5t by 6 to 1.8. I got my t hat to be 6 times 1.2 by 1.45. Is that okay? So I guess a lot of people wrote 36 by 25. So 36 by 25 is also, I think, correct answer. Okay. I hope you work this out. The same thing now for ML. Okay. Can you verify your answers for estimation? I gave you the answer just now for method of moments for this problem. I'll show you the answers I have after a little while. I'll let people work it a little while. Maybe there's not too much time we have left, but there are some 4-5 people who are working it out. So I'll give a couple of minutes, then we'll go through. Oh, okay. 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 Is it possible to verify the correctness? So one way of doing it is, if you do MM and ML, you should sort of get similar answers. If your ML and MM are giving very different answers, then maybe something is wrong, right? So that's one mild hint you can try. So basically estimate using multiple methods and see if you're getting sort of similar answers. That could be one way of doing it. Or you should get valid answers. For instance, for this case, this is 1 minus t by 2, right? Supposing my t ends up being 3, what happens? I got 1.45 here, I was happy. But my t cannot be 3, What will happen if I got a t hat as 3? Likely that something has gone wrong in my estimation. I shouldn't give 3 as the answer. You see why? Why should I not give 3 as the answer? So 3 gives me a negative probability for x equal to 3, right? That's doesn't make sense. So you cannot have 3 and all that. So if you get some absurd answer like that for the parameter, then you know something maybe went wrong. Okay, let's quickly see the answer. 36 by 25. A lot of people have got 36 by 25, 1.8, 1.6, 9 by 5. Okay, all right, let's see. Let's see what solution I have. The solution is the likelihood function is t by 3 power 4 times t by 6 power 4 times 1 minus t by 2 power 2. Okay. I sort of collect the constants together and the variables together. I get t power 8 minus t squared by some constants. Okay. I take log. I simply keep a constant term here for all these denominators. What's interesting is 8 log t plus 2 log 2 minus t. Okay. And then I differentiate equal to 0. I get my t hat ml as 1.6. Okay, I saw a few 1.6 out there. I think that's pretty good. If you got 1.6 or 8 by 5, maybe I saw 9 by 5, that could be some minor bug or a mistake, but 8 by 5 is largely the correct answer. Okay, so you see 1 point here. You remember what you got for the MM estimate? You got 1.45, right? So you see 1.45, 1.6, sort of ballpark, similar numbers in some sense. Okay, so I have one more estimation problem. This is a more textbook estimation problem. You might even remember it from the way from the lectures. It's a geometric P distribution. 4, 5, 7, 3, 6, 5, 4, 5. Find the MM estimate. So one more way in which, Aniket, you can maybe try and explain if the estimation is correct or wrong is to sort of see if after you found the parameters value, do the samples look like reasonable samples from that distribution? Okay, supposing for instance you're finding P here, right? Supposing P comes out to be 0.001, right? Okay, let's say P is 0.001. Your estimate is 0.001. Is it likely to be a correct answer? No, right? I mean, samples are like 4, 5 and all that. And you're getting 0.001 for P, that will give you samples of 1000, right? So something is wrong. So that kind of thing also you can do to check your answer if you want. Okay, so let's quickly see the responses. A few of them have come in. 8 by 39, 8 by 39, 39 by 8. So 39 by 8 is clearly wrong, right? Again, I said, P is a probability. You can't have 39 by 8. These are all quick ways of checking and making sure that you don't make mistakes. 8 is the sample mean, but P is 8 by 39. So 8 by 39 is correct. If you got 8 by 39, that's good. Okay. The same question, same samples. You have to find the likelihood function and the ML estimate. Okay, that's the next question. Okay, the answer itself might be quite quick. Maybe the likelihood function is taking a little time. In the interest of time, let me just go through and do it very quickly. You will get 8 by 39, 8 by 39 39 will be the answer. Let me just show you the solution real quick and sort of quickly walk you through it. It's not terribly illuminating or difficult or anything. It is just okay. So the first thing is very trivial. 39 by 8 is 1 by p. So geometric distribution mean is 1 by p. So p becomes 8 by 39. Again, remembering these things, if you're not the habit of remembering the mean of geometry, you should have the table with you, the table of distributions. Okay. So the ML estimate for P, probability of geometric distribution taking value 4 is 1 minus P power 3 times P times minus P power 4 times P for 5 times minus P, so on, minus P power 4 times P for last 5, right? So if you multiply these things out, you're going to get 1 minus P power 39 minus 8. How did I get 39 minus 8? For each of the samples, the 1 minus P gets raised to the power, that's sample minus 1, right? So sample minus 1 plus sample minus 1 plus sample minus 1, the sum minus 8. Then P gets raised to the power 8. So you just get 31 log 1 minus P plus 8 log P. So you just differentiate, equal to 0, you're going to get 8. Okay. So I in fact, I did this in the one lectures as well. So this is just a straightforward thing in some sense, but it's good to practice this. If you're doing it for the first time, I agree. I'm going at a slightly fast pace. Apologize for that. We're a little bit late, so let's go to information. Okay. Sort of the last question. The last question is beta distribution. The mean 2 by 2 plus b. The beta has two parameters, a and b. The first a has been given as 2, and next you have the b of this beta distribution is 2 by 2 plus b. Is that okay? 2 by 2 plus b. That's an interesting question. How were these methods invented? So the method of moments is very, very old. Maximum likelihood goes back to Ronald Fisher. Okay. So I think you should read this book called The Lady Tasting Tea. Okay. Let me just title down. The Lady Tasting Tea. What does this have to do with statistics, you may ask? Search for this book, okay? It's sort of like a historical account of major statistical ideas and who created them, where did they come from, what were the origins, and very intuitive, very good book. It's available, I think, on Amazon or something. The Lady Tasting Tea, okay? Search for that. I think maybe somebody can post the exact link to that title. It's a pretty popular book, very nice, intuitive. Too expensive, is it? Real? I seem to have a copy which says paper book or something. I didn't think it was so expensive. Okay, so people are taking a lot of time over this. We don't have too much time. Remember, the mean is just 2 by 2 plus b. So you find the sample mean, or maybe finding the sample mean is a bit hard. You have to add up all these things and divide by 5. Okay, so you do that, you get the sample mean and equate it to 2 by right? Is that right? That's what you do in method of moments. There you go. 1993 apparently. So maybe what you can do, you get together with your group members, there are 20 of you, or maybe enough friends, buy a book and then, circulate. So your cost gets divided by 100 if you find 100 people like that. Right? And then you only pay 20 bucks. 20 rupees. So I think that's an option if you like. It's a very good book. I've enjoyed. Don't do this. Okay. PDF drive downloads. Please don't do that. I'm not a fan of these things. Do it secretly in your secret groups. Don't do it in a group where I am. Okay. Anyway, that's a long. All right. So let's see the responses. I think 0.52 is the sample mean. 1.84 or 5 looks so okay. I think that looks fine enough to me. Okay. So let's go to the part B, which is a gamma distribution. Gamma A comma 5. Gamma again has two parameters. The mean of the gamma distribution is A by 5. Okay. The mean of the gamma distribution is A by 5. All right. And there are 5 value samples that are given. Find the sample mean, find the method of modeling for A. It's clearly 5 times the sample mean in some sense. It's a quick answer. Okay, so you see method of moments estimate for even complicated distributions is very easy. So I don't know how much you're keeping up with the lectures. You see the lectures, doing ML estimation for gamma and all is quite complicated. You need numerical algorithm methods. It's a bit more complex than you can imagine. Very, very quickly and very. Okay. So I think this is probably the easiest question out there. Okay, 0.39. Yeah. Just 5 times the sample mean is what you have to do. It's great to see that. Okay, good. I think we're running out of time. A lot of people have got the correct answer here. Good to see that. So I have my solutions too. I can quickly show that to you. And yeah, it's left the answer of fractions here, 2.39. Yeah, the answer is basically the sum of the values. You're right. I picked a very, very, very simple and particular case. Okay, so the last problem is a little bit lengthy and it's a little bit of a challenge question in some sense. It's not that complicated, but you may get a very surprising answer. So I put here a distribution which is slightly unusual. It's a continuous distribution. The PDF is ax plus 1 by 2a plus 2. Okay, and x takes values between 0 and 2. Okay, so this is the ax plus 1 by 2a plus 2, and x takes values between 0 and 2. This is a valid PDF. You can check that this is a valid PDF. Ax plus 1 by 2a plus 2. A is the parameter. Okay, and here are samples. I've given you 5 samples, and see, so first thing you should notice here is ax plus 1, isn't it? So a cannot be smaller than minus 0.5. You agree? Okay. A cannot be smaller than minus 0.5. If a becomes like minus 1, then this PDF will go negative. So it will become invalid, right? So a has to be greater than minus 0.5. Okay. Yes, I think Shruti's idea is very good. So A becomes greater than minus 0.5. So what will happen if you do estimate is you will get a value for A which is below minus 0.5. Okay. So these are things that can happen sometimes in estimation problems. When those things happen, you have to be very careful. When you have a limited range for A, you should not give an absurd answer of A being outside. If it's minus below minus 0.5, you simply give minus 0.5 as the answer. Okay. So this is what will happen in this problem. In this problem, I've given an ML also. I'll put up the solution. You take a look. I don't go through this problem in great detail here. You can try to solve it. I've put in the answer, I'm getting minus 0.618, and that's sort of meaningless in this question. I need to be minus 0.5, so I can say minus 0.5. Same thing will happen with ML. If you do ML with just 2 samples, minus 14 by 5, that's sort of an absurdish answer. So you should revert back to the answer. Okay? So why does it happen? Because you're blindly relying on the samples, and really the samples are a bit too far away from the actual distribution, and this happens. It's very rare samples. So in those kind of cases, this can happen. Okay? So I'll leave you to look at it anyway. The 12th problem is sort of a bit of slightly advanced problem. I don't want you to worry about if you get it. The problem is so Manish is asking about week 8. Have I not covered week 8? The estimation problems are all from week 8, right? Isn't it? So whatever it is that we looked at in week 8 and week 7 is what is the topics that are relevant for the exam. And I think that has been given to you. There was some question about what about topics in week 6 and week 5. Week 6, week 5 are fully included, right? Only week 7 and 8, there is a subset of topics that we have chosen. And these are the topics that you have to pay attention to from week 7 and week 8. Okay. So that sort of brings us to the conclusion of this session. So let me stop sharing. Thanks a lot once again for participating in this. Week 5 and 6 were already covered, yeah. Thanks for staying up late, and as usual, ended a little bit later. I hope that's okay. All the very best for the exam. I know it's a long day. A lot of you have asked.
Sir,
I mean, I mentioned about a 7-hour exam coming up. Yeah, I think it's a long exam. All the best. I hope you do well, and I hope you have a good time. And do well, prepare well, you will do well, be positive, back yourself, work hard, and things will be fine. Okay? Thank
sir,
you very
just
much,
one,
and good night.
sir, just one question, sir.
Maybe you can send me an email, Samit. It's quite late.
Okay, sir.
Okay?
Okay, sir.
Okay. 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 Thank you, and good night. Bye-bye.